All right, we're going to finish up this chapter with 2.6 here, and we're going to look at limits that involve infinities, and then therefore looking at asymptotes of graphs. So what we need to do is first define and investigate infinite limits, and then we're going to use them to find vertical, horizontal, oblique asymptotes, which is something we were finding back in pre-calculus and in algebra and stuff like that. But here we're going to find it using limits, and we'll do a little more algebraic tools for this stuff. So don't forget the symbol for infinity is that little sideways 8 like that, and it doesn't represent a real number. So think about what it actually does describe. It's more of an idea than it is an actual number. So we're not going to treat it like it is just an actual number. So kind of get your mind wrapping around that no matter what number you come up with, it's always bigger than that. So it isn't just an actual number. All right, take a look here. Definitions, we say that f of x has the limit L as x approaches infinity, and we write it like that: limit as x goes to infinity of f of x equals L. If for every number epsilon greater than 0, there exists a corresponding number m such that for all x, x is greater than m, implies that the absolute value of f of x minus L is less than epsilon. So that's going back to our limit definition. And we also say that we have a limit as x approaches minus infinity, and we write it like that, where x goes to negative infinity of f of x equals L. So we can go to infinity, which isn't an actual number, but actually then get a limit as we go to it. And you can kind of see that here in this graph right here, where this is the graph of 1 over x, and you see as we go to infinity, right here, as we go out to infinity, we're just going to keep getting closer and closer to x equals 0. And if we go towards negative infinity this way, we're just getting closer and closer towards x equals 0 as well. So we're approaching the 0 value there, but we're not really going to quite reach it, But as we go bigger and bigger, we just keep getting closer and closer to it. Okay? So let's take a look here at the next page. For the function f, whose graph is given, determine the following limit. So we're just going to pick these out off of here. So this is something we were doing before. So the limit of f of x as x goes to 2. So here's 2. As we go to 2 from both sides, we're going towards 0 from either direction. Maybe I need to do that in a different color. Let's put that in red. So as we're going toward this way, and as we go toward it this way, we're approaching that value of 0 right there. So this is just going to equal 0. The limit as x goes to negative 3 from the positive side. So here's negative 3 right here, and we're going to go toward negative 3 from the positive side. So that's from here. And as we do that, we're approaching negative 2. So this is equal to negative 2. Here, the limit as x goes to negative 3 from the negative side. So again, there's our negative 3, and we're going from the negative side, so we're coming from the left. And as we do that, and we keep approaching, we're going towards this value there, which is positive 2. Next, just the limit as x goes to negative 3. Well, it's not an endpoint. It's not like the edge of our, it's not the edge of our domain. So both the left and right limit have to match. The left and right limits that we just did in B and C do not match. Therefore, the limit there does not exist. All right, a limit as x goes to 0 from the positive side. Well, that's coming down right here, and we're going up, and we're pointing right toward that negative 1 right there. So this is going to be a negative 1. The limit as x goes to 0 from the negative side, well, here, look at what we're doing. We're going and blowing up, right? Like that. And so we don't have any boundary on that. This is going to be a does not exist, goes to infinity. And then the limit as x goes to 0, that's going to be a does not exist because the left and right limits there do not match. Now let's look at the limit as x goes to infinity. That means we're coming out this way. And as we do this, we're approaching that value 1 right there. So it'll be 1. And as x goes to negative infinity, we're swooping down this way, and we're going to 0. We're getting toward that x-axis, so y will equal 0. Okay? So go through those, make sure you think your way through them, and understand them. All right? So now, evaluating limits at infinity. Theorem 12. All the limit laws in Theorem 1 are true when we replace limit as x goes to c by limit as x goes to infinity, or limit as x goes to negative infinity. That is, the variable x may approach a finite number c or plus or minus infinity. So here, the limit as x goes to plus or minus infinity of k is still just k. That was one of our limit rules. Remember that one, very important. The limit of a constant is just that constant. And the limit as x goes to plus or minus infinity of 1 over x is 0. We saw that in our graph on our first page. All right. The limit of 5 plus 1 over x is just the limit of each of those. So it's going to be the limit as x goes to infinity of 5 plus the limit as x goes to infinity of 1 over x. And this will just be 5, and this will just be 0. So it's just 5. The limit of this one here, pi times square root of 3 over x squared. Well, we're just taking the limit of the two things, so we can actually break this up really into three things. The limit as x goes to negative infinity of pi times square root of 3, that's just a constant. And then we can make this 1 over x and 1 over x, just like that. And then we could just do the limit of each one individually, the limit of this one, the limit of this one, the limit of this one. I'm not going to write them out each individually because that's just going to be 0. That's going to be 0 from right here. And then that other one is just the actual constant. So it's pi square root of 3 times 0 times 0. And so that just equals 0. Okay? I'm going to add a little something in here. Limits of polynomials over polynomials. Limits of polynomial of degree n over a polynomial of degree m. So if you remember this from algebra, from pre-calculus, we had rules for determining asymptotes based on whether or not the polynomial in the numerator was greater or less than or equal to the degree of the polynomial in the numerator. And so if we're thinking of that, remember we had our three situations. One where the numerator was greater than the denominator, and so that would give us the limit goes to infinity, because the numerator is always going to be greater than the denominator, which means we're going to end up with a very big number. Example of that would be something like x squared plus 3x divided by x minus 1. Okay, so something like that. That's going to go to infinity as you go to, the limit's going to go to infinities as you go to plus or minus infinities, depending upon whether or not, you end up with something, it could be, I guess, plus or minus infinities, depending on whether or not you have an overall odd or even degree. And then here we can do n equals to m, the numerator equals the denominator. This is going to give us a horizontal asymptote. Okay. And it'll be according to the ratio of the leading terms. And then the last thing we can have is n less than m. And when that happens, when n is less than m, you can end up with a horizontal asymptote. And this one will be at y equals 0. Okay? And that could be just x minus 1 over x squared plus 3x, the reciprocal of that first one we did. Okay? So keep this idea in mind. I know it was stuff we did before, but hopefully it'll kind of make a little more sense as we start talking about limits as we go forward here. So limits at infinity of rational functions. First off, what you're going to do is divide every term by the highest power of x in the denominator. The highest Okay, so when we take a look at this, we have the limit of 5x squared plus 8x minus 3 over 3x squared plus 3 plus 2. And so what we're going to do is divide every term in the numerator and the denominator basically by that. But in order to do that and keep it the same, you do it for both. So we can do this as times. Our highest term here is x squared in the denominator. So this is going to be 1 over x squared and 1 over x squared. So multiplying by 1 over x squared is dividing by x squared. And when you do that, what happens is you end up with the limit as x goes to infinity of, now 5x squared divided by x squared is just 5. 8x squared divided by x squared is just 8 over x. And negative 3 divided by x squared is 3 over x squared. In the denominator, you get 3x squared divided by x squared is 3 plus 2 over x squared, just like that. And then as you go to do these limits, these ones that are over top of x's, they just go to 0. So this is going to go to 0, this is going to go to 0, this is going to go to 0. And all we're left with is essentially, as we take that limit, 5 plus 0 minus 0 over 3 plus 0, which is just 5 over 3. And that's where we're going to end up with our asymptote here. And you can see it here in this graph down here, right? It's we have this line of y equals 5 over 3, this line right here, and our graph is going to be approaching it but never crossing it. And then same thing going the other way. All right, so let's take a look at the next one. The highest term we have in the denominator is cubed, so we can do times 1 over x cubed in the denominator and 1 over x cubed in the numerator, and we'll end up with the limit as x goes to negative infinity, and in the numerator we're going to have 11 over x squared plus 2 over x cubed, just distributing that in. In the denominator, we're going to have 2 minus 1 over x cubed. And so everything that's over an x is going to go to 0 when we take the limit. So this is just going to be 0 plus 0 over 2 minus 0, which is just 0, ultimately. All right, as we take that limit, put my equal signs here, equals, equals, equals. Okay? This is just 0. And you can see if you do this graph right here, it's going towards 0 here as we go to, actually we were going to negative infinity, so as we go to negative infinity, it's just going right towards 0. All right, I'm going to leave these two for you to try. Do the same thing that we just did before in the previous page and see what you come up with, and I will finish it up in the notes, and you can take a look and compare it. Next, horizontal asymptotes. If the distance between the graph of a function and some fixed line approaches 0 as a point on the graph moves increasingly far from the origin, we say the graph approaches the line asymptotically. So, and that line is an asymptote of the graph. So a line y equals b is a horizontal asymptote of the graph of the function y equals f of x if either the limit as x goes to infinity of that function is b, or the limit as x goes to negative infinity of f of x is equal to b. So if either one of those is true, we consider that line to be an asymptote. Okay, so it's kind of a little more formal definition or way to think about asymptotes is that our limit goes to that value. You know, we always talked about, it always approaches the horizontal asymptote, but never quite gets to it. Now we're saying, the limit of it becomes that because we're approaching it, which is what our whole idea of a limit is. So find the horizontal asymptote of the graph x cubed minus 2 over the absolute value of x cubed plus 1. So we need to calculate the limit as x goes to plus or minus infinity. And so let's take a look here. First, let's take a look at the limit as x goes to infinity. Here what happens is all of our x's are positive, so this would be x cubed minus 2 over the absolute value of x, then cubed, plus 1. And here, as we go to positive infinity, all of our x values are positive, so if you cube a positive number, you get a positive number. So we can just ignore that absolute value because, well, one, we're taking you're taking the absolute value of a positive number. So this just becomes x cubed minus 2 over x cubed plus 1. We do what we did before, multiply by 1 over x cubed on the top and 1 over x cubed on the denominator. And we'll end up with the limit as x goes to infinity. I didn't write an infinity there. As x goes to infinity of 1 minus 2 over x cubed over 1 plus 1 over x cubed. And these two terms are going to go to zeros, and we'll end up with 1 over 1, which will just be 1. All right, so there is our limit as x goes to infinity. Notice that these all keep turning out to be just the ratio of the leading terms whenever we have the same, the degree matching on the top and bottom. Next, let's try limit as x goes to negative infinity. Here, we've got x cubed minus 2 over absolute value of x cubed plus 1. But since we cube a negative number, you get a negative number, right? Negative 1 cubed is negative 1, negative 2 cubed is negative 8. It maintains that negative sign. We can leave the top, x cubed minus 2, but what we have to do at the bottom, because we're taking the absolute value of it, is we have to take the opposite sign. So in other words, like say this was negative 2 absolute value cubed, that would equal, we could do this as negative of negative 2 cubed, like that. And those two would then ultimately turn out to be the same, because this would be 8 and this would be 8 as well. So we can put a negative sign in front of it to get rid of that absolute value. So this would be negative x cubed plus 1. Okay? And when we do that, we can do the same thing. You plug in, multiply by 1 over x cubed and 1 over x cubed on the top and bottom like that. And ultimately you're going to get 1 over negative 1, and you just get negative 1 there. Okay? And so basically we have two horizontal asymptotes. One is at y equals 1, and one is at y equals negative 1. Let's take a look at e to the x, a graph we should be fairly familiar with. Here, what we're doing is taking the horizontal asymptote of it, and we're going to take a look at what happens as we go toward negative infinity. And if you look at the graph, as we move toward negative infinity, we're going to be going towards 0. And you can try this by plugging in different values of x. So like e to the negative 10, I think you end up with like 0.0000045, and then e to the negative 100 is going to be even smaller, more decimal places, and e to the negative 1000, I mean, that's 1. Remember, this equals 1 over e to the 100. So e to the 100 is big, 1 over e to the 100 is small, and e to the 1000, e to the negative 1000 is an e to the 1000, and e to the 1000 is big, so 1 over that big number is even smaller. So this is just getting closer and closer to 0. And then the limit as x goes to infinity of e to the x, well, here, this is just going to blow up. We're not taking any reciprocals. It's, it's e to the 10, e to the 100, e to the 1,000, e to the million. It's just getting bigger and bigger and bigger. That one's going to go to infinity. All right, so here are our two limits as we go in those directions for that. So we do end up with an actual horizontal asymptote for e to the x, and it's at x equals 0. Okay? An algebraic tool. We are able to switch variables if we are careful with our limits. So let's take a look here. Let's take a look at the limit as t goes to 0 of 4 times the sine of 6 minus 6 cosine of 10t. Just like that. Over 6 minus 6 cosine of 10t. Okay? And if we look at that, what we can do is we can say something like, and I'll put this part in red, is we can say let u equal 6 minus 6 cosine of 10t. Because in this situation, it looks like we could make this go a little bit better. And so this would then be, remember that as t goes to 0, what's u going to do? And as t goes to 0, u is also going to go to 0 because it's 10t in there, right? It's going to end up being, as t goes to 0, it becomes what? It's 6 minus 6 cosine of 0 as t goes to 0, right? And then that just equals 0 because cosine of 0 is 1, so it's 6 minus 6, it's 0. So as t goes to 0, u goes to 0. So we just have to kind of see what is going to happen with our new limit. And so because of that, we can replace this whole thing with limit as u goes to 0 of 4 times the sine of u over u. All right, and that's one that we should be able to do. We can bring the 4 out in front. Limit as u goes to 0 of sine u over u. And that whole limit is just going to be 1, and so this is just 4. All right. Remember that sign, that limit right there. This one right here is one you're supposed to know. Okay. So there you go. All right, I think I'm going to stop there for this video. The next few pages I'm not going to worry about. We're going to just kind of skip over that one. We'll skip over this one. We don't need to do that. And that would include this too. We can skip that. And then in the next video, I'll pick up on the next page. Okay, that's it. Thanks.